Today we're going to go over implicit differentiation. Now, this is a bit of a difficult topic to teach because it's so unique. What people are typically used to is explicit differentiation. Now, this is also called normal differentiation. For instance, if I were to give you the equation y equals x squared, the derivative of this using explicit differentiation is y prime equals 2x. That's what you're usually used to. However, implicit differentiation differs from this. Typically with implicit differentiation, you are finding the derivative of an entire function rather than a specific variable, rather than the dependent variable, for example. And oftentimes it's difficult to isolate the dependent variable. Oftentimes it's intertwined with the independent variable. And occasionally the final derivative will feature both the dependent and independent variable. So I'm going to give you an example of one instance of implicit differentiation. Let's say x squared plus y squared equals 5 minus y. Now, as you can see, it's a bit difficult to isolate y. There's no good way to do it. So with implicit differentiation, you end up taking the derivative of both sides, usually with respect to the independent variable, in this case being x. And you just simplify it from here. You end up with 2x plus this term over here, the derivative of this term, but I'll get to that in a moment, equals the derivative of 5, which is 0, minus the derivative of negative y. Okay, so let's get into this. The derivative of y squared, which I'll write over here, isn't equal to 2y. In fact, you have to employ the chain rule to find the derivative of this. The secret to doing so is by in your mind. This is what I use. In your mind, replace the y with an x and derive normally. So for instance, we're going to just replace it with an x and then derive it, replace it back with y. We end up with 2y. Except what's different about implicit differentiation is you also have to write at the end what you've just derived with respect to the dependent variable. So 2y isn't, the derivative of y squared isn't 2y, it's 2y dy dx. And in fact, this is equal to y squared, and so this is more your derivative, if anything. So I'll write that over here. The derivative of y squared is 2y dy dx minus negative y. And as you can imagine, this is negative dy dx because we're deriving this term over here as if it was with a y rather than or with an x rather than a y, which would be negative 1. And of course, we have to write dy dx near the end. Now, to simplify this, we can say that 2x equals dy dx negative 1 minus 2y. We can simplify that further by saying this whole function, the derivative of y with respect to x is equal to negative 2x over 1 plus 2y. And that is our final answer. And that is essentially how you use or how you derive implicitly. Okay, this is practice problem 1. I should have stated that this, rather than finding the slope, we should be finding the equation for the slope. Nonetheless, let's get into it. We're going to find the derivative of the term on the left. That is, of course, 2x equals the derivative of the term on the right. Now, as I said earlier, we're gonna replace y with x, and then after deriving or differentiating, replacing it with y once more. So what is the derivative of sine x? Well, it's cosine x. It's pretty simple. However, as I said, we're going to have to replace this with x. So the derivative of sine y, we're going to have to replace this back with y. So the derivative of sine y is equal to cosine y. And if you'll recall in the beginning of this video, I said that you have to throw a dy dx on at the end. So the derivative of sine x is cosine x, the derivative of sine y is cosine y dy dx. So we'll write that over here. And we can isolate the term dy dx such that we end up with 2x equals cosine y. And I failed to mention this earlier, but you're going to start treating terms like dy dx algebraically. You may not have done this in the past, but it's what you're going to have to do from here on out, or at least when you're dealing with implicit differentiation and whatnot. Okay, I'd like to preface this section of the video by stating that if you're ever concerned when to use implicit differentiation, don't worry, because AP exams, AP tests in general, will make it blatantly obvious when to use implicit differentiation. Okay, so now let's get into the the practice problem 1. We're asked to write an equation for the line tangent to natural log y plus x equals y squared at 3, 4. Now this is pretty simple. In fact, let's change this. Rather than adding the 2, let's multiply the 2. Okay, so we have to find the derivative of both sides with respect to x. Let's start off with the right side, because the left side is a bit more complicated. The derivative of y squared is 2y dy dx. And the derivative of the right side is a bit more difficult. So to find the derivative of natural log y times x, we're going to have to employ the product rule. Now, there's a mnemonic, not necessarily a mnemonic, but there's a way to memorize or to memorize the formula for using the product rule. 1d2 plus 2d1. That being that we multiply the first term times the derivative of the second plus second term times the derivative of the first. So 1d2, natural log y, times the derivative of x, which is 1. So that part is quite simple. Plus the derivative of the second term times the derivative of the first term times the second term, which is x, times the derivative of natural log y. I'll write that down here. So the derivative of natural log y with respect to x is a bit not necessarily complicated. As I've told you many times, the technique for finding the derivative of a term with y is to simply just replace y with x, derive it, and replace y later. So the derivative of natural log x is going to be, of course, 1 over x. We'll replace this one with a 1 over y and slap a dy dx on there. So the derivative of natural log y is 1 over y dy dx. Okay, so we have the derivative of our function. And now we just have to isolate some of the terms and turn it into a tangent line formula, which won't be too difficult. So we'll move this term over here to the left of the equation. And from there, we can simplify it further by taking out the dy dx. So we end up with dy dx times 2y minus x over y is equal to natural log y. And you can probably imagine what we're going to do from here. We're going to divide each side by 2y minus y over x. So we end up with dx dy equals natural log y over 2y minus x over y. All right, so now we just have to find the tangent line at 3, 4, at point 3, 4. This is not too difficult. Hopefully you remember the formula for a tangent line. Y minus the y coordinate equals the slope, which we'll just mark this with a question mark for now, times x minus the x coordinate, x minus the x coordinate. So now we just have to find the slope at 3, 4. This is our equation for the slope at any point. From here, we just have to fill in our values. So the y at 3, 4 is 4, as you would imagine, over 2 times y, which is 8, minus x over y, which is 3/4. And this can be simplified further, but I don't feel like it. So that's it for today's video. If you have any suggestions, please leave them in the comments below, and thank you.